Okay then, so what we want to do now is understand what the final sort of important symbol for doing topos theory is, which is the exists uh, arrow or exists notation in the Mitchell-Benabou language. Um, so there is a way of interpreting it directly in the Mitchell-Benabou language. That's how Colin McClarty defines it, and he defines there exists x in A such that phi, he defines it like this, okay? But I find that a bit cryptic, so I prefer Goldblatt's definition, which is in terms of, using sort of epimono factorization. So just a quick reminder how to do epimono factorization. Basically, if you have an arrow f from A to B, you can sort of, in a topos at least, you can sort of chop it into a epic and then a monic. So the way that you do this, if you write your arrow like this, then you can form a push out. So that's a push out square. And then if you get the equalizer of these two, well, I should call them I's actually, not P's, since they're more like injections than projections. But the thing is, now you can find the equalizer of those. And the equalizer we can call IMF, and it's like the image of F, and it's part of his epimono factorization. Now, if you write, well, normally we call this object f of A. Now notice that P1 after F is P2 after F. So although we define this to be the equalizer, if we have the actual F here, which is going to be going from A to B, then there exists this, because we know that P1 after F is P2 after F, we know this equalizes P1 and P2. And therefore there has to exist this unique arrow, which it turns out is actually an epic like this. And a good name for this, I think, is F restricted to F of A. Something like that. Doesn't really matter what we call it, but this gives us our epimono factorization of F. Now, so okay, we know that, but how we're going to use it. And this is all, by the way, this stuff I'm saying now is all very well described in Goldblatt's book, Topoi, the Categorical Analysis of Logic. Anyway, like if we're dealing in sets, this FA we could just think of it as a collection of B such that there exists an A such that FA equals B. And then we can just think of the IMF as an inclusion function. Anyway, let's go to more general topics. So this is an interesting thing. If we have the truth arrow, we're working in general topos, of course, and if we pull that back along the evaluation arrow for the power object, we get this thing that we might call in A. Now I'm putting a little g as a superscript here because this is how Goldblatt defines it. Colin McClarty actually puts a twist in his definition of this in monic. But anyway, so the point here is that, like, we can think of this, like say we're dealing in sets, we can think of this as the sort of collection of subsets of A, and if we pair that with an element of A, when we evaluate, we find out is that element in that subset or not. That's what gives us our true or false here. And then if you think about what the what this means, since we're saying that E is the classifying arrow of this in arrow here, this in arrow, this sub-object, is really selecting all of the kind of subset element pairs such that that element is in that subset. So that's why I write it like this. It's sort of isomorphic to the collection of subsets of A, if we're working in set, of course. A collection of subsets of A paired with an element of A such that the element is in the subset. Anyway, consider this sort of epimono factorization. So we already have this sort of Goldblatt in arrow, followed by the projection. So that's going to send us, it's basically going to take one of these pairs where we've got a subset with an element, then think of that as part of omega to the power of A times A, and then find the first entry from that, so it just extracts a subset. Now we can do an epimono factorization of that. So this sort of epic part is not really too important. Well, I mean, it is actually. What it does, it sort of finds the collection of sets, subsets of A, which actually have one of these subsets containing elements sent to it. Okay, so really, this is, if we're dealing in sets, this is the collection of non-empty sets, non-empty subsets of A. All right. And then this is just the inclusion function, just including those. That's our sort of monic and our epimonic factorization. So what we can really think of this arrow as doing is just selecting all of the sort of non-empty sets from here. And hopefully you can see that this should have something to do with the notion of like an existential quantifier, something that can tell us if elements exist or not. So let's suppose we have this arrow here. So this is, I suppose we can call it IM of P1 after Goldblatt's in arrow. So it's the image of that. So I mean, what this is really doing is, if we're dealing in sets, is it's injecting, it's a sort of sub-object consisting of all the non-empty sets. Now, this there exists A thing is just defined to be the classifying arrow of that. So all it's really doing is it's sending all of the non-empty sets to true and the empty set to false. Okay, so we basically, when we do there exists after like a set, as in an element of omega to the A, we're really just determining, does that set have elements or not? I mean, if it's not empty, then this is going to yield a true value. Okay. I mean, we can see this quite easily. If we do an arrow like this, then we're going to have that there exists an A after U is going to be true if and only if U is in this collection V of non-empty sets. Okay. Right, so given that, let's define this existential quantifier. Now, I should say that this inference that we can define the existential quantifier like this is really my own kind of guesswork. I must admit I'm a little bit green to using like the existential quantifier in particular, and I have not proved yet that it's equivalent to McClarty's definition, but I believe it is, and it certainly seems to be logical, etc., etc. So when we're working with, like in the Mitchell-Benabou language, I think we can define there exists an A dash in A such that phi, where phi is some formula, and we can say that's equivalent to saying there exists capital A after this set builder notation, so set of A dash in A such that phi, okay? But we're not really talking in set theory at the moment, and this curly bracket stuff is just shorthand for this lambda notation. So this is what we really mean. We mean there exists capital A after lambda A dash of phi. Okay. So let's try and understand why this kind of notation seems to make a lot of sense. So, like, what's the let's suppose that phi is some kind of a term which has a free variable from capital A and a free variable from B. So, for example, phi could be, I don't know, say GA equals GA dash equal, well, it doesn't matter. It doesn't matter if we use A dash or A, but it could be this. Okay. For example, where A and B are variables from objects A and B. Anyway, we're interested in, like, what's the interpretation of this. So notice that because we've got this lambda operator, this A dash variable is bound to the lambda operator. So the only free variable is this B here. So the interpretation of this term is as an arrow, since it's a type omega term, as in it's kind of given as a logical value. Its interpretation then is going to be as an arrow from capital B to omega, and it's like this. There exists a dash in A such that psi of A dash comma B. And these square brackets here, this stuff is sort of my own notation just to remind me that phi has, in this case, we're imagining it has three variables involving something from A and something from B. Okay, so the point is really how do we interpret this? And we interpret it as the composition of these two arrows. So it's the set of A dash in A such that phi of A dash comma B interpreted with a B before doing this exists arrow. That's what this is. So in other words, it exists A after this arrow. And then what we're really interested in is like when does doing this arrow after some sort of generic H element beta of B give us a true? In other words, when is beta belonging to this extension of the load of B such that there exists an A dash with phi of A dash comma B. So that's obviously equivalent. Beta being in that subobject, that extension, is equivalent to saying that if we do this interpretation of this arrow after beta, we get true. But what does that mean? Well, we can we know what this exists A dash stuff means according to my proposal. It just means we can just put an exists A on and put the curly brackets in. So that's what we do here. And we're saying this is true. So the point here is that, so I just want to talk now going to the category of sets. I mean, I believe you can use all this epimono kind of factorization stuff to work out what's happening in more general topoi. I mean, in particular, you just need to know how to calculate co-limits. Well, limits are easy. You just need to know how to calculate co-limits in your topos, and then you can do the epimono factorization. And at least in pre-sheaves, I describe how you can calculate co-limits in general. So you can do that kind of epimono factorization. You can calculate the push out involved, do it, so then you can get your exists arrow and you can build all this stuff and do all the logic. But anyway, for comprehension, I just want to talk about what's happening in sets. So I've already sort of argued that when you have there exists and then some arrow into omega to the power of A, sorry, there exists after some arrow into omega to the power of A, like this one here, blah blah sets after beta, then you're going to get a true when you do the exists after that stuff. You're going to get a true if and only if this curly brackets blah 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 beta is a non-empty set or corresponding to a non-empty set. So what I'm saying is that beta is going to be in this extension if and only if the set of A dash in A such that phi of A dash comma B, or interpreted with a free variable B, doing that after beta gives a non-empty set. Or another way you can say it, if you want to get rid of a set builder notation, you can replace it with a lambda, and then you can actually use the Mitchell-Benabou rules to evaluate it, and what you end up getting is that there exists an A such that the transpose of the interpretation of phi over B comma A dash after beta is true. Now we can really understand what this means. So if we just assume that beta is a point of B, well then what we have here is just, like, let's say we've got an A in there as well. Well, this phi is going to give us a true when we do this phi thing on beta and A dash, we get a true. But what's going on over here? Well, we're leaving RA alone with this arrow because we're times it by 1A, but what we're doing to the beta is we're replacing it with a set of A dash such that phi A comma B close curly brackets after beta. So that's where we send our beta, and then we leave RA alone, so we've got that stuff after beta, comma A, and then we evaluate. But how does that evaluation arrow work? Well, basically the way it works is it, like generally, this in set at least, this evaluator from the power object is just going to give a, so what we're going to be evaluating on is going to be a subset of A paired with an element of A, and he's going to give us true precisely when that element is in that subset. But notice also that we need this diagram to match up. I mean, also you can see that E works like that, or you can kind of gain evidence from it by considering this diagram and how this works. So, I mean, basically I was saying that this in that this Goldblatt in subobject thing is basically selecting the sort of pairs of a subset. I mean, in set again, it's selecting the pairs of a subset with an element such that that element's in that subset. In other words, this is a subobject classified by this evaluation arrow, which I've just described. Anyway, the point is that now we can understand what this means, what transpose of phi after beta is, because, like, if we go this way around the triangle, we just get our beta and A and just do phi on it. So we're just finding out, is phi true when we use this value of beta and this value of A. But if we go this way, we convert our beta into this kind of subset of A, which is called transpose of phi after beta. And then when we pair that with an A and we evaluate, we want to get the same result as we do with this left arrow. So that means that what we're really checking, and we know what we're really checking is whether this A is in this particular subset we get. And so what we can really think of this as, this interpretation of collection of A dash such that phi A dash comma beta all after beta, such that phi comma B all after beta, we can think of this as the collection of A's which are going to be in this phi relation with this beta here. Okay, so in other words, if we put this, if we're thinking about, so it's really so what this transpose arrow is really doing is it's sending a beta in B to the set of, or I should say maybe the subset of elements of A which are in this phi relation with that particular B. Now that's cool because now we can understand what this means. Because what this is saying is that this collection of A, which are in this phi relation with beta, is non-empty. In other words, there exists an A which is in this phi relation with this particular beta. And that makes sense, right? Because what we're saying is that beta is going to be in this extension. This is what the notation says. Beta is in this extension when there exists an A such that, or an A dash in this case, just a different dummy variable, but when there exists an A dash such that phi of A dash comma B. Okay? So this all makes a very lot of sense. Now, I've used various kind of... So anyway, let me just talk through this again just to make sure that this is clear. So what we're saying is that doing this evaluator after all of this stuff, so after this curly brackets A dash such that phi of A dash comma B stuff with a beta, doing that and also paired with an A, that gives a true if and only if phi of A comma beta is true, and that's going to be if and only if A is a member of this thing, interpreting it as a subset. But here E is this classifying arrow which sort of tests. So in general for here I'm talking about a global element of omega to the power of A. We have that E of theta comma A is true if and only if A belongs to theta. So this curly bracket stuff with a beta on the end is the set of A such that phi of A comma beta is true. And then since beta is in this extension here, if and only if this curly bracket stuff after beta is non-empty, we have that beta is in this extension if and only if the set of A such that phi of A comma beta is true is non-empty, which is true, which is the case if and only if there exists an A such that phi of A comma beta is true. So that's a little bit of light shed on this there exists arrow. Now let's talk through more of this stuff of interpreting Goldblatt. So when we have a formula phi, in other words, a type omega term, this extension here of the phi dash, such that phi, of the x bar such that phi is defined to be the sub-object classified by the interpretation of phi over when we're using these free variables in this list x bar. Now we say that phi is true when this sub-object here, this extension, is the identity. And we use this gamma sometimes to denote a list of formulas. And we define the extension x bar such that gamma to be the intersection of the x bar gamma 1, x bar such that gamma 1, x bar such that gamma 2, etc. I believe we can calculate the intersections pairwise, in pairwise fashion. When we don't have any formulas on the left, sorry, when we don't have any that's not what I meant to say. Let me just double check this. Sorry, yeah, that's what I thought. When we don't have any formulas on the right, I should say, this extension is just defined to be the full sub-object, as in the identity arrow, of A1 times blah 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 AN, where we're assuming that x bar is this list of free variables x1, x2, well, variables, ... and we have that x1 is a variable of type A1, x2 of type A2, etc. We say that gamma implies phi when this extension using a gamma is contained in this extension using a phi. When this list x bar lists exactly the free variables of gamma and phi. A sequent is something written like this: gamma colon phi, gamma dot phi, and we say this is true if and only if gamma implies phi. But I mean, generally, we can think of this as a sort of proposal and we can infer things from it. But when we know it's true, we write this sort of gamma long turnstile phi. So we've got that nothing implies phi. I'll say definitely implies when we have this long turnstile symbol. So nothing definitely implies phi. That's the case, I think, if colon phi is true, which is the case if this extension here, phi extended over the x bar, is equal to the identity. And that's the case if we'll sometimes say phi is true. When one sequent A infers a sequent B, we write it like this, with a a horizontal line, so A horizontal line B, reading downwards, and star denotes the empty set of assumptions. So we can consider the Mitchell-Benabou language purely in terms of sort of manipulations involving these symbols, these terms. And that's one very nice thing about it. And these are sound and they're complete in the sense, or I believe they're complete in the sense that we can infer any kind of formula which is true for any topos. Now, I mean, particular toposes like sets and things have special features, special facts which are true in them, and we may not be able to infer those from this language. But we can infer all the stuff that's true in general. Anyway, what are the rules? Well, we have this sort of trivial rule that we can start with this sort of no assumptions, and for any formula phi, we can always get phi implies phi. Again, starting from nothing, we can always get that nothing implies true and that false implies anything. Okay. FA means false, interpreted as a term. We can also do this thinning operation. So if we have that gamma implies phi, then we know automatically that gamma and psi implies phi. So here we've just got a list of formulas, but we'll see later that we can really think of this as an and, I think, if at least if it's on the left. Yeah, when we've got a load of common formulas written on the left, I mean, that's how we interpret them, basically, as sort of intersecting the extensions, which I think is equivalent to just putting and symbols in here. And sometimes I write an and as a, so we could write this like this, for example. I use this sort of ribbon shape to mean and. Sometimes I try and draw the ampersands, but I'm not very adept at it. So anyway, this is thinning. Basically, it just means that, you know, when we know that gamma implies phi, adding in some extra assumption on the left, we still get phi implied. Substitution as well. So when we have a phi, if we have a a variable x and a term s of the same type, then we can write, for example, phi or x/s. And what that means is replace each of those variables x with this term s. That s needs to be free in x to be able to do this. I think I've got this right. And we're allowed to do this substitution. So whenever we have gamma implies phi, we're allowed to substitute in like particular terms, not just using these sort of generic variables. We also have this cut rule, which turns out to be very useful. So what this basically says is if we know that gamma implies psi, well, I mean, if we're supposing that gamma implies psi and also that gamma and psi imply phi, then we know that gamma implies phi. And then we also have these different so-called reversible connective rules. So these double lines here mean that we can go from the formula on the top, from the expression on the top to the expression on the bottom. And when we have two things on top, we can go from the bottom to either of the ones on top as well. We can infer things in both directions when we have these double lines. So there's 4 different connective rules. C1 is involving false. So it says that saying that gamma and phi imply false is equivalent to saying that gamma implies not phi. So this is not. Second connective rule says that gamma and phi imply psi is equivalent to saying that gamma implies that phi implies psi, where here we're using this implies using the arrow. So we're talking about implies as a kind of black arrow. So that would be the thing that has the, this is a logical well, I mean, the real meaning of this is that arrow after we should say arrow after phi comma psi, where this arrow here is the subobject classifier of less than or equal to 1, as I've discussed in the past. But I mean, this formula really, this expression really gives us a way to go between what this double dot thing means, and this kind of implies that we can express normally. So I've just got a bit of discussion of this. So phi arrow psi is true if and only if arrow after phi comma psi is true if and only if chi of less than or equal to 1 of phi of psi is true if and only if phi comma psi is in less than or equal to if and only if phi is equal to phi and psi, if and only if phi is at least as true as psi. And you could go even further. We could say that's also if and only if the subobject classified by phi is contained in the subobject classified by psi. I'm sort of mixing notation here. These are actually terms, but I'm just interpreting them as arrows, kind of wrongly, but just to, I mean, at least in this latter case, you'd have to actually say, well, what are you interpreting these terms over, etc. But anyway. So that's one interpretation of this. Another way to think of it is that gamma infers phi implies psi basically means that the extension over gamma is contained in the extension over phi implies psi. Or if you like, the subobject classified by the interpretation of gamma is contained in the subobject classified by the interpretation of phi implies psi, which is phi star double arrow psi star. And we know that that holds true if and only if phi star intersection psi star is contained in psi star. And then we can write that as extensions like this, which is true if and only if phi and psi, if and only if gamma and phi implies psi. So we've got that. We've sort of proved this connective rule 4 here. Anyway, I've talked about connective rule 1 involving false, so I could sometimes call this the false rule. C4, I could call it the implies rule. There's a couple of others. C2 is the and rule. So it says that when gamma implies phi and gamma implies psi, then gamma implies phi and psi. We could write this stuff here. As and phi comma psi. But anyway, and then finally we have the or rule C3, which is saying that when we have that gamma and phi imply theta and gamma and psi imply theta, that's equivalent to saying that gamma with phi or psi implies theta. And finally, we have a couple of extra rules involving these existential quantifiers. So we have the saying that well, when x is not free in gamma or psi, we have that writing gamma implies phi is equivalent to saying gamma implies for all x phi, and similarly, when gamma and phi imply psi, that's equivalent to saying that gamma and there exists an x such that phi implies psi. We also have a few sort of so-called axioms of local set theory, but for us they're not really axioms, because all this stuff can be proved. But this is one which is that basically nothing implies, or it's always true that for every variable of type 1, so in other words for any y from the terminal object, y is equal to exclamation mark. Now exclamation mark is defined to be the basically the identity arrow of the terminal object. So this is basically just saying terminal object has one thing in it. We also have some equality axioms. So for any q, r, and x of type A, these variables, we have that q equals q is true. And also if q equals r, then the expression we get when we replace x with r implies the expression we get when we replace x with q. We also have this sort of biconditionality arrow law, which is saying that when v implies w and w implies v, we have v equals w. Sometimes that's written as vw double arrow w, or v's equivalent to w. We also have this kind of so-called axiom, which is involving how the product works. So these are product projections down. We have P1U equals P1U dash, and P2U equals P2U dash implies U equals U dash. And we also have that P1 after S comma S dash is S, and second projection gives us S dash. And this is extensionality. What this says is that when it's true for all x dash in A, that f of x equals g of x, where I'm using this round bracket notation to mean we're evaluating things. So we've got f and g are actually of type b to the power of a, so these are sort of ready to evaluate functions, and when we do evaluate them for x, we always get the same result for any x. That means f equals g. And then we also have this sort of axiom of comprehension, which is basically saying that lambda x dot a of s, evaluating that on x, equals x. So I think that should be equals s. Yes, it should. So that's basically just saying that our exponential objects work properly. When we're dealing with sets, we write the extensionality axiom like this, because the equal sign becomes a double arrow sign. These kind of evaluation things with the round brackets, we use this in notation again instead, so it becomes like that. In a similar way, the comprehension axiom looks like this when we're dealing with formula. And that's it. Now, I think I should just say briefly um, that the OR operator, when we're talking about it in terms, like as a term, we can say phi or psi is equivalent to saying that for all W, we have that phi implies W and psi implies W, implies W. I think we can also define false as for all WW in terms of terms, but the way I prefer to think of it is that false here is the classifying arrow of the arrow from the initial object to the terminal object, and not is the classifying arrow of false. Anyway, let's look at some example deductions.